past. Okay, so I think let's slowly get started. If we have more people joining later, then that's probably okay. So today I want to say thank you to Jason for joining us and coming to give a talk. We're really excited, and for getting up so early. It's early in Berkeley. Jason is currently a postdoc at the Simons Institute in Berkeley, and he just finished his PhD, I think, at CMU.
Yep.
And he has lately been doing a lot of very exciting work on graph algorithms, and I guess we'll hear a lot about it now. So I'll say that and leave it at that. So thank you, Jason.
Right. Thank you, Rasmus, for the introduction. So this talk will be on this new technique called isolating cuts and its applications for min-cut algorithms. And most of the, can I start now?
Yeah, sorry. Yeah, sure. Go ahead.
Okay. So most of this work was done with Demelia Panagraki at Duke, and these slides are by him. Okay. So in this talk, we'll be considering mostly min-cut algorithms on graphs. So formally, this is defined as given the graph, find the minimum cardinality or weight cut, satisfying some condition about disconnecting vertices from each other. So, for example,
by the way, Jason, I think we're not seeing we're kind of seeing an open PowerPoint window rather than like.
Oh, okay. Let me share my screen instead of my. I'm sorry. Give me a second.
Oh, don't worry. Sure.
Didn't realize. Is it better? Is it better?
Yes, now we see it. Yep. Thank you.
Great. Thanks. Okay, so in this talk, we'll be considering various min-cut problems on graphs. So this is formally defined as given the graph, find a minimum cardinality or weight cut that satisfies some good condition about disconnecting vertices from each other. So for example, the most natural definition is to disconnect any two vertices from each other, which is the global min cut. In this case, the global min cut is 1 because we can delete the middle edge and separate the graph into two parts, disconnected pieces. And throughout this talk, we'll only be considering undirected graphs. So min cuts can be defined for directed graphs as well, but for this talk, we will only consider undirected graphs for the talk. But the graph can have parallel edges, as in it can be a multi-graph, or it can have non-negative edge weights, which means it can be a weighted graph. So, for example, the first two graphs here are allowed for this talk. This is a multi-graph, and this is this is a weighted graph. But we will not be allowing directed graphs in this talk. So once again, the most natural min cut definition is just a global min cut. There's no additional constraints. We just want to disconnect some two vertices from each other. For example, once again, in this graph, we just delete the middle edge to disconnect the graph, and that's the minimum weight global min cut. Another natural definition, a variant of min cut, is the ST min cut, or you can think of it as a more local version of min cut, where we're given two particular vertices, S and T, and we want to disconnect them. And the classic Maxlow min cut theorem says that this can be done by computing an ST Maxlow. So for example, in this picture, if you take S and T1, then since S and T1 belong on different sides of the global min cut, their ST min cut will also be the same. But on the other hand, if you pick S and T2 on the same side of the global min cut, then the cut will be different because the global min cut no longer disconnects them. In this case, the ST2 min cut is just this cut right here. And one less well-known min-cut variant, but also generalizes both ST min-cut and global min-cut, is the Steiner min-cut, which is we're given a set of terminal vertices S, and our goal is to separate some two terminal vertices from each other. So for example, if the terminals are just S and T, then this is exactly the ST min-cut. And if a terminal set has all the vertices, then this is the global min-cut. So once again, if S is the set S, T1, and T2, then once again, the Steiner min-cut is also the global min-cut because that disconnects, say, T1 and T2. And sometimes we're not just interested in a single min-cut, but we're interested in computing multiple min-cuts. So for these problems, we can, for these settings, we can define a single source min-cut, which is for a fixed vertex S called the source. We want to compute for all other vertices T and ST min-cut. And the most powerful variant is the all pairs min-cut, where you want to find for all pairs S and T the ST min-cut. So what do we know about these min-cut problems? How can we relate them to each other? Well, one simple trivial fact is that the global, Steiner, and single source min-cuts can all be computed using n-1 calls to ST min-cut, or equivalently, n-1 calls to ST max flow, right? Because you can just fix a vertex S and try all other vertices T, or all other terminals T in the Steiner case, and one of the vertices T must be on the opposite side of the target global or Steiner min-cut, and so one of the choices is will return you either the global or Steiner min-cut. Now, what about the all pairs min-cut? The all pairs min-cut, you can actually do better than just computing all pairwise min-cuts. It can be done using just n-1 calls to min-cut.
Jason, I think you cut out for a second and it sort of made the screen disappear.
I'm sorry, is my internet spotty? The connection is spotty?
There was no issue, but now the screen disappeared for us. Like we don't see the shared screen anymore.
You see it now?
Give it a second.
Should I reshare screen?
Yeah, I guess maybe reshare.
Sorry about this.
Oh, well, it's not your fault.
Now? Is that good?
Now I think
you see it now?
Yeah, now we see it.
Okay. So what about the all pairs min-cut problem? So miraculously, Gomery and Hu showed that you can actually do better for the all pairs min-cut problem than just computing n squared many ST min-cuts for all S and T. This can be done in using just n-1 max min-cut computation. Now, if you plug in the current fastest max flow algorithm, this gives you a running time of roughly mn plus n to the 5 halves for randomized and this time for deterministic for these problems. So you can think of this like worse than mn. It's like at least mn time. So like you think of mn as like a benchmark, and these are slower than mn time. So for the naive n-1 max flow calls algorithm to solve these problems.
Jason, I'm sorry, but now it happened again somehow.
Okay. Okay. I guess I'll just keep on resharing screen whenever it happens. I guess there's no.
Yeah.
It doesn't take much work.
It works. Yeah.
I also realized there's delay. There's like a several second delay. That's like as in like either way a few seconds before I can hear you talk. But maybe that's just the fact that we're on opposite sides of time.
I don't know. It might also just be that I'm responding slowly because each time you reshare the screen, it takes a few seconds before I start to see it.
Okay. So let's plot the current. So let's plot various algorithms for these problems. So the naive one just takes n minus one max flow calls. Now for the global min-cut problem, there is an mn time deterministic algorithm. This was independently discovered by many groups. And finally, Carter invented a near linear time algorithm for this problem, randomized for global min-cut, and this essentially resolves the complexity of global min-cut for randomized algorithms. But until the work study in this talk, MN was the best deterministic algorithm known. Okay. So this is a landscape of all the known results before our work. So there's you can think that there's 3 tiers of problems. The first tier is all pairs min-cut, single source min-cut, Steiner min-cut. All these, nothing better is known than just the trivial n minus 1 ST min-cuts. And this is their corresponding running times. The second tier of problems is the ST min-cut, just the ST min-cut, which is just one max flow call. And finally, the third tier is global min-cut. And for global min-cut, there's a significant separation between deterministic and randomized. Okay, so let's actually focus on the bottom 2 tiers first. And what's interesting here is that global min-cut is faster than ST min-cut for randomized algorithms, but slower for deterministic algorithms. So in other words, there's no true relation before this work comparing global min-cut and ST min-cut. One is not any easier than the other in a reduction sense, because the complexity are different for randomized and deterministic. So this is one kind of relation that we'll address in this talk. Okay, so let's focus on that problem for now. In particular, let's ask the question: can we obtain a deterministic global algorithm that runs as fast as the deterministic ST algorithm? So in other words, can we show that the global min-cut is actually strictly easier than the ST min-cut, both for randomized and deterministic algorithms? So for this problem, or for more general global min-cut, deterministic global min-cut problem, no progress was known since the MN time algorithms until 6 years back, where in a breakthrough, Karwich and Thorup gave a deterministic algorithm for simple graphs in near linear time. And this paper actually recently won the Fulkerson Prize for it. This running time was subsequently improved. Some polylog particles were shaved. But until then, nothing was known for general weighted graphs. So all these results only hold for simple graphs. So in this talk, we discuss the first improvement on this problem for weighted graphs. So this result is by myself and Damalia Panagrahi. We show that there's a deterministic algorithm for global min-cut problem using polylog and ST max flows, or ST min-cuts. So this once again, this establishes a strict relation between the two problems. This shows that global min-cut is actually easier than ST min-cut. And it turns out, just half a year later, I had a result that fully resolved the deterministic global min-cut problem. I showed it ran in almost linear time. But for this talk, we'll be focusing on the first result here, because it introduced a new technique called isolating cuts, which will be the focus of this talk. Okay, so let's move on to our main idea, isolating cuts. So here's a brief roadmap of the next third of this talk. We'll be introducing the isolating cuts, and we'll show how the isolating cuts can be used to derive a very simple randomized min-cut algorithm using isolating cuts, global min-cut. So this shows, at least for the randomized case, global min-cut is only easier than ST min-cut. Now, in our paper, we also next step is to de-randomize the randomized construction. This one is done using expanded decomposition. It's fairly technical, and we will not be covering this talk. So we'll only consider the randomized one, which is very simple. Okay, so let's first introduce the new idea, isolating cuts. And before we introduce, let's motivate why such a problem came, why we studied such a problem in the first place. So let's recall the global min-cut algorithm again, which uses the naive one, which uses n-1 max flows. So what it does is it fixes a vertex S and just tries all other vertices T, one of which must lie on the opposite side of the target global min cut. Now, of course, it's doing this naively because all it really needs to do is locate one vertex T on the other side. If you can find one vertex T, then we're done because the SD min cut will be the global min cut. So essentially, the task is just to find two vertices S and T on opposite sides of the cut. And the question is, can we find such a pair more efficiently than just trying all n-1 vertices? So one simple observation is, let's consider the structure of the target min cut. So let's fix the optimal global min cut and let's see what kind of structure does it have. Well, first of all, if it's balanced in the sense that both sides of the min cut have, let's say, a constant fraction of all the vertices, then we're in good shape, at least in the randomized setting, because we can just sample a random S and random T. With constant probability, S and T will lie on opposite sides of the min cut. So this is a trivial algorithm that takes like only log n many ST min cuts. Now, suppose that more generally, the smaller side of the min cut has k vertices. So now think of k as like root n. I like to think of k as like root n. So not too small, not too large. Then what can we do? So we cannot sample S and T at random anymore. But let's do something very simple. Let's do a different kind of sampling. Instead of sampling two vertices at random, let's independently sample for each vertex. We sample it with probably 1 over k. So here we're kind of guessing k. Let's say we guess k as the powers of 2. And for some k that's like close to the actual k, the number of vertices on the smaller side, let's see what happens. So the scenario that we want, the ideal scenario is we sample vertices in such a way that the smaller side of the min cut, the side with k vertices, has exactly one vertex that's sampled. So this actually happens with constant probability if we select the right k. And as we'll see later on, this essentially sets us up for the isolating cuts procedure. So once again, we're subsampling the set of vertices, and what we want from the subsampling is exactly one vertex on the smaller side of the min cut is sampled. And this happens with constant probability for an appropriate value of k, which we can guess, let's say, all the powers of 2. Okay. So, of course, we're not done yet, because while the smaller side has only one vertex, the larger side still has many vertices. So we cannot. So far we cannot reduce it to just a small number of ST min cut calls. So here's a picture of like the current setting. So suppose that S comma V minus S is the target min cut. Now let T be our sample set, and in this case this is like a success condition where this is a successful sampling where exactly one vertex in S was sampled. Okay, so if we successfully sample, we've essentially reduced ourselves to the following problem. We're given a graph and a subset of T of vertices, and we want to find essentially the min cut that separates some vertex in that sample from all the other vertices in the sample. Of course, we don't know which vertex is isolated from the rest, so we kind of just try them all. So we want to find for each vertex T and T, each sample vertex T, the min cut that separates that vertex from everyone else. And we want to do this for each T because, again, we don't know which T is isolated. So one other way that you can think of this is contract all the vertices aside from T into like a single supervertex S, and then it just becomes an ST min cut. So this is exactly what it means to find the isolating cuts. These are the cuts that isolate some vertex T from the rest of the vertices. And so we call this the isolating cuts problem. Okay. So naively, we can compute the minimum isolating cuts for all T using the size of T max locales, because we can just loop over all T and compute the ST min cut. Of course, this is useless in general because, again, the size of T can be large. But our core lemma for the isolating cuts is that we can actually do much better. We can solve an isolating cuts problem in just log n many max locales. And we'll see a full proof of this lemma. We'll see we see most of the proof, the proof of this lemma in this talk. It's quite simple. Okay, so but before we move on to the proof of this lemma, let's see how it implies a very simple randomized global min cut algorithm. So recall that let's fix some target min cut in our head. Once again, we guess the value of S. So we choose like some k equals 2 to the I, where I ranges from like 1 to log n. We guess within the factor 2 of the correct size of S. And then we just sample vertices independently, probably 1 over k. And with high probability, if we form log n samples on each of the scales, and with high probability we'll be at the situation where exactly one vertex from a smaller size is sampled. And this is like just a standard Chernow bound, not even Chernow bound, standard union bound kind of argument. And then finally, we apply the isolating cuts lemma on each sample. That means that for each sample, we get a bunch of isolating cuts, one for each terminal. And then over all the samples, over all the isolating cuts, we just output the minimum sized cut out of them all. And that's our algorithm. So this is a very simple, once again, it's a very simple randomized global min cut algorithm. And the pretty much the only extra trick aside from minimum isolating cuts is random sampling. Okay, so now let's give a brief proof of the quick proof of the isolating cuts lemma. There will be one step we'll hand wave a little, but aside from that, it'll be a complete proof. So here's how the algorithm works. Once again, the goal is to solve minimum isolating cuts using just log n SE max locales. So what the algorithm does is it first encodes each vertex, each terminal. Think of the vertices T as terminals. Each terminal vertex using a binary string, a different binary string. So this takes like log of size of T many bits. And now the point of this encoding is that we want to output some log n many bipartitions of the terminal set. And the way we'll do that is for each bit position, partition the terminal set into two parts based on whether the kth bit on each vertex is 0 or 1. So think of like k as a power of 2. So this is like an equal sized bipartition for each k. And now once we have these bipartitions, the first step of the algorithm is to find a min cut that separates xk from yk. And this, once again, this can be done by contracting each side into a single vertex and calling ST max low. So here's a picture for the case when there's 4 terminals. So there's 0, 0, 0, 1, 1, 0, 1, 1. And then here is one for the first bit, the blue bit. This is our separation. This is our partition, the top and bottom. And for the red bit, this is our separation, left and right. And now what does the algorithm do again? It computes a minimum cut that separates two sides for each of the bipartitions. So think of these as the cuts we get. And now one important property of the way we chose our bipartitions is that for any pair of terminals, they are separated by at least one of the bipartitions. That's because the two bit strings cannot be equal. We've chosen them to be all different. Therefore, they must differ at some bit, and they will be on different sides for that bit, for the partition corresponding to that bit. So because of that, that means that if we imagine taking these ST cuts and deleting them all from the graph, then in the remaining graph with the min cuts deleted, every connected component has at most one terminal. It can have 0 terminals, but it cannot have more than one terminal because they must be separated by one of these cuts. Okay. So in this case, imagine these are the 4 components we get, and indeed each component has at most one vertex. At most one terminal. Okay. So now we're left with, we're essentially left with like a bunch of disjoint connected components of the graph, minus the min cuts. And now from here, we want to get the set of isolating cuts. So the next step is for each set Si, define Si to be like each of the connected components in the graph minus the min cuts. We imagine contracting all the vertices not in Si. So for example, so imagine contracting all the vertices not in Si into a single super vertex, call it Zi, and call the resulting graph Gi. So now in this graph, let's compute a Ti, Zi min cut using a Maxwell call. So for example, in the case where S3, for the case when I is 3, let's take all the vertices not in S3, we contract them all into a single super vertex called Zi, and we compute a T3, Z3 min cut using a single Maxwell call. And we do this for each I. Any questions for so far? Okay. So the first claim is, so first of all, what can possibly go wrong in the graph contraction step? Well, it could be that the isolating cut actually has at least one edge being contracted, and therefore it's no longer a valid cut in the contracted graph. That would just kind of destroy the correctness of the algorithm. But we claim this cannot happen. So essentially, the contraction step is safe. It does not destroy the target isolating cut. So equivalently, the claim is that the Ti, Zi min cut in G is Ti, T minus Ti min cut, is an isolating cut for Ti. In other words, we can essentially take the cut, expand the other side, the contracted vertex Zi, to the original set of vertices. This is still a cut, and it will be the minimum isolating cut for Ti. So this is the part where we won't prove. It's like a two-line argument, but it uses a standard technique called uncrossing of the. It uses a standard property of uncrossing for min cuts. The fact that if the cut did have edges contracted, then we can perform a kind of uncrossing argument and show that there's a different cut that is equally as good, still minimum isolating cut, that is not contract. That has no edges contracted. So again, I'll skip this. This part is pretty standard application of uncrossing, so I'll skip this part of the proof. Now, second question. So this shows correctness. Now the second question is how about running time? So at first glance, so how many max? So what about running time? First step is we've computed some log t many bipartitions, and for each one we made one Maxwell call. That's just log t many Maxwells. And the second step, at first glance, it seems like we're actually computing a t Maxwells for each of the sets G. For each of the contracted graphs Gi, we're making one Maxwell call, and so that's overall t many Maxwell calls. So where are we saving the running time? The key observation is these graphs are not small on average. In fact, the total size of all of the contracted graphs is roughly the size of the original graph. So more precisely, in the over all the contracted graphs Gi, there are only like O of m edges total. So why is that? That's because every edge in the graph is either one of two possible. Every edge in the graph is either completely contained in some Si, in which case it only appears in that corresponding Gi, because in all other Gis that edge must be contracted, or if it connects between two different Sis, in which case the only time when this edge survives is for the graphs the only time where this edge survives if we pick one of the SIs one of the SIs containing one of its endpoints. So there's only at most 2 SIs in which this edge survives. So overall, every edge appears in at most 2 of the contracted graphs. So that's like 2M total edges. That's any questions? This essentially completes the proof.
I think it's very clear. Thank you, Jason. Let me just mention to the audience, I'm paying attention to the chat. So if they have questions there, I'll tell you.
Okay, great. Okay, so that essentially completes the isolating cuts algorithm. And now, and also that completes the isolating cuts algorithm, and also the global min cut algorithm that uses isolating cuts. And now, one immediate observation of the global min cut algorithm is that it does not use any specific part of the global min cuts. So in other words, I claim that this global min cut algorithm can also be generalized to solve Steiner min cut. All we need to do is begin with a set of Steiner vertices instead of all the vertices. So once again, the main idea for global min cut was to sample a set of vertices where we want exactly one vertex on the smaller side of the min cut, and then use isolating cuts. Well, Steiner min cut is just essentially the same problem, except we can just start with a set of set of terminals and do the same sampling. And once again, with high probability, one of the samples will have exactly one vertex sampled in Steiner min cut. So we can essentially run the same algorithm to solve Steiner min cut. So here is the concrete theorem that we show. We show that we can solve not just global min cut, but Steiner min cut. Okay, this is a mistake. This should be randomized. There's a randomized algorithm for the Steiner min cut that uses log cubed and Maxwell calls. And the surprising thing about this theorem is that before our result, no non-trivial algorithm was known for Steiner min cut. So while global min cut was solved by Carter, he got a near linear time randomized algorithm, nothing randomized or deterministic was known for Steiner min cut, the general case of weighted graphs, that ran in even just like sublinear number of Maxwell calls. So we brought it down from linear Maxwell calls all the way down to polylog Maxwell calls. And the algorithm is just surprisingly simple. It's just percent random sampling plus plus the isolating cuts. Right. So now let's go back to this landscape and see what changes between these 3 tiers of problems with our new result. So before that, one consequence of the other result that I did not cover in this talk, which is the almost linear time global min cut algorithm, is that global min cut is now just almost linear time deterministic. But what does change from the isolating cuts algorithm is that we've essentially moved Steiner min cut from the top to the bottom. In other words, SD min cut and Steiner min cut are now essentially equivalent up to this polylog factor. So in other words, we've moved Steiner min cut from the first tier, the highest tier, to the middle tier. And we established an equivalence between these 2 problems. Okay, so here's a more graphic view of the setting. So first of all pairs min cut is definitely the hardest. So one non-trivial reduction that I not described yet is that all pairs min cut can actually. Oh, I'm sorry. Wait. So all pairs min cut is definitely the hardest problem, and then single source min cut is strictly easier, or is at least is no harder. And then once again, Steiner min cut can only be easier, and finally global min cut is just a special case of Steiner min cut. And the isolating cuts algorithm essentially it's establishing equivalence between these two problems, where previously it was just one single error. So another cool equivalence statement is that actually the top 2 algorithms are equivalent, and this was first shown by Aboud, Krautler, and Trabelsi, and we also touched on this in I also touched on this in a paper with Demaya Panagrahi. Okay. So now the current landscape is just there's only essentially different tiers instead of 5, where the top two are equivalent, these two are equivalent, and the easiest one is still equivalent. So here, essentially, this is the new tier of problems. But 2 questions remain. So the first question is, can we bridge the gap between the first 2 tiers? In other words, is there a single source maker algorithm that's faster than the naive one of running just, let's say, SE mincut n-1 times? Now, ideally, this will be, if it can be done using polylog n time SE mincuts, then these 2 will be equivalent. But that's like a very ambitious goal. So let's relax the goal for now and say, can we even beat the non-trivial algorithm? Can we even do anything non-trivial? So any less than n-1 Maxwell's. So that this would attempt to bridge the gap between these 2 problems. And for the second 2, the problem really boils down to, is there a linear time Maxwell algorithm? Because global mincut is linear time, both randomized and deterministic. And to make these 2 equivalent, we essentially need the ST mincut to be also near linear time. But that's also a very big open question in graph algorithms. Is there a linear time Maxwell algorithm? So once again, these 2 are very difficult problems. And solving them completely will be a huge deal. Okay, so let's actually visit the all pairs mincut problem now. Once again, Garmer and Hu gave a remarkable algorithm that showed that you can do better than just computing like all pairs ST mincuts. It suffices just to compute n-1 ST mincuts. And what is equally surprising is 6 years later, this remains a state-of-the-art problem, at least prior to work in this talk. Of course, there's definitely been a lot of attempts to break this barrier. In particular, faster algorithms are known for many restricted graph classes, but for general undirected weighted graphs, nothing better is known. Okay. Now, one thing that one equivalence that helps in the search for fastest algorithm is the equivalence between all pairs mincut and a single source mincut. And so in other words, to improve all pairs mincut, it suffices to just show single source mincut. But on the other hand, prior to work in this talk, nothing for single source mincut was known, aside from just the n-1 trivial, the trivial n-1 Maxwell's. On the other hand, if we could improve that, then we could improve Garmer tree in particular, and also all pairs mincut. Okay, so I will talk about the improvement later in this talk. For now, let's consider a different direction that also attempts to make some progress on this problem, which is approximations. So since exact all pairs mincut has resisted attempts for 60 years, let's consider what if we relax the condition to just wanting approximate all pairs mincuts. So for this case, we can ask 2 very similar questions. Is there a 1 plus epsilon approximate all pairs mincut algorithm that's faster than, let's say, running exact SE mincut that's 90 times, n-1 times? So this is essentially the most relaxed version that you can ask for these 2 problems. And similarly, you can ask a similar problem for these 2, which essentially boils down to, is there a near linear time algorithm for 1 plus epsilon approximate SE mincut? So a beautiful line of work due to Sherman, Kellner, Lee, Orekia, Sidford, and Richard Peng show that this 1 plus epsilon approximate SE mincut can indeed be solved in near linear time. So this essentially closes this problem in an approximate setting. Now, one result that by myself and Panagrahi answers the top question also in the affirmative. So it turns out if we relax the problem to do 1 plus epsilon approximation, then we can actually solve it in polylog many exact SE mincuts. And so here was the theorem. here's a statement that we can use this minimum isolating cuts framework to get a algorithm to find 1 plus epsilon approximate ST min cuts, all pairs min cuts, using just polylog and exact Maxwell calls. And this algorithm actually outputs a Garmin-Hu tree, so it even solves that problem. And you can just plug in the best Maxwell algorithm, and you get something that's like better than MN time. So it breaks the MN barrier for these problems, and it computes all pairs 1 plus epsilon approximate min cuts. So one immediate question asked is, why do we require exact Maxwell calls? So I only touch on this briefly, but the reason is because in the isolating cuts proof, there's this uncrossing step, which we show that, which I kind of hand waved the fact that the isolating cuts must be contained in this contracted graph, must survive the contraction. If we replace the max flow oracle in the isolating cuts with the approximate ST min cut, we replace the ST min cut oracle in the minimum isolating cuts algorithm with approximate minimum isolating cuts, then the uncrossing step no longer holds. And that essentially kills the isolating cuts procedure completely. So in other words, the isolating cuts procedure does not work with approximate ST min cut as an oracle. And therefore, this is why we require exact min cuts. So in the past year, there's been actually many applications of those isolating cuts. So for example, we found applications for vertex connectivity, essentially the vertex min cut. We showed a faster all pairs min cut in simple graphs using this technique. And we even show the problem of faster connectivity augmentation and edge splitting off using isolating cuts. So this is like three quite different problems that all use isolating cuts as a core routine. Of course, there's many different new ideas. They feature other ideas on top of that, but isolating cuts was really like the main driver that made this possible. Okay. So in the last few slides of the talk, I'll be considering like very new recent results. So these are results that have not been published in conferences yet, but some of them are posted on arXiv. So the first result is, let's touch upon this problem of, do we really need exact Maxwell calls to solve this 1 plus epsilon approximate all pairs min cut? Once again, this is kind of undesirable because we're using an exact oracle to solve an approximate problem. So let's ask this question again. So it turns out this is almost true. So in unpublished work by myself, Nanankai, Panagariki, and Saranarak, we show that this is almost true. So we can almost compute 1 plus epsilon all pairs min cut using 1 plus epsilon approximate ST min cut. The one caveat is we need a special variant of 1 plus epsilon approximate min cut that I will not. It's a bit technical. I will not go over how it works, but it allows for this isolating cuts framework to work by strengthening the requirement of the oracle. And we also solve this oracle problem in nonlinear time. So the final result is we actually get a 1 plus epsilon approximate all pairs min cut in nonlinear time. So this essentially collapses these two problems. But once again, this is not like a strict this is not a full reduction in the sense that we're not really reducing to just 1 plus epsilon approximate ST min cut. We're reducing something stronger that we can still solve in linear time. So the second result I want to briefly touch on, again, this is unpublished work. This one's actually posted on arXiv. Is let's go back to the problem of comparing all pairs min cut with ST min cut. So once again, the problem is there a single source min cut algorithm that is faster than just naively running ST min cuts n-1 times? So in very recent work, it was posted on arXiv, I think, early this month. We can actually also improve on this. We can show something non-trivial. So we showed that n to the 7/8 sublinear number of min cuts suffice this problem, and therefore also for all Paris-Smith and Garmin tree. And this is essentially the first improvement of this problem in 60 years for general graphs. Once again, the isolating cuts is a core component of this topic. Of course, that's so essentially like this kind of essentially has resolved like many of the questions in this talk. The real one main like outstanding problem that would be huge if solved is, can we bring us all the way down to like sub polynomial number of ideally logarithmic, ideally polylogarithmic, but even sub polynomial would be huge. So is there can we close this gap all the way down to sub polynomial? And this will essentially collapse these two tiers of problems into one. And so that concludes my talk. Thanks for listening.
Thank you very much, Jason. So we have a question in the chat. Max asks, can you maybe sketch how to get global min cuts from isolating cuts deterministically?
Oh, okay. Okay. Is there a whiteboard app I can use, or
I suppose if you have anything, you could share it.
I can share like an MS Paint if there's no better option.
Yeah, I think so.
Okay. Do you see the screen, or am I sharing a window?
We see the presentation still.
Okay, let me share. Let me share. Okay. So yeah, there's definitely something non-trivial going on in the deterministic de-randomization, because once again, when the min is actually balanced, like it has a constant number of variables on both sides, this is actually like somehow the hardest. It's trivial for randomized because we just sample S and T, but it's actually what like intuitively it's like the hardest for de-randomization, because how are we going to find S and T on both sides? So the trick is actually so one tool will be expanding decompositions. But let's ignore that for now and just consider like what is a high level strategy. So high level strategy is as follows. So essentially, so let's say we have a bunch of vertices, and we have our target min cut wherever it is. So the high level strategy is we want to do like a vertex sparsification of the terminals. So here's what we would like to do. So we have our terminal set, and we have our target min cut, which we don't know. Our goal is to sparsify the number of terminals by half. Let's say, essentially, we want to deterministically pick, let's say, half of the number of terminals. We want to do it in such a way that we still have at least one vertex on both sides of the min cut, because otherwise, if we don't, then we're dead. Right? We cannot find this cut. So does that make sense? So we want to do this kind of terminal sparsification, and we want to do it iteratively. So do one at a time. Do it. Have it at each step. And now what we can show is that, first of all, we divide the two cases. We divide into two cases. The first case is suppose the target min cut is unbalanced, in the sense that it might contain more than one terminal vertex. First of all, if it contains one terminal vertex, then we just do isolating cuts. It can contain slightly more than one vertex, let's say polylog vertices. In that case, I claim we can still de-randomize the isolating cuts procedure. The reason is because we can subsample with probably like 1 over polylog n, and this can actually be de-randomized. So if we sample with just 1 over polylog n probability, then there's actually efficient de-randomization. And the overhead is like polynomial in the inverse probability. So like 1 over, so it's essentially a polynomial of this polylogin. So that can actually be de-randomized. So the case that can be de-randomized is that there's a most polylogin versus on the smaller side, terminals on the smaller side. So now what if there are more than polylogin vertices? Then here the trick is we do some kind of expanded decomposition, and the intuition of why this. So in this case, the algorithm is just computing expanded decomposition, and within each expander, pick like an arbitrary selection of a small number of vertices. And we show that if the min cut is balanced, as in it has a lot of vertices on both sides, like more than polylogin, then this for sure will still hit at both sides. Like we will still for sure have at least one verse on both sides. And okay, the rough intuition on that is because like, so if you have a bunch of expanders, the global min cut cannot cut deeply into each expander. You cannot have things like this. You must like kind of like essentially agree with the decomposition. And if it does that, then like if we sample like a small number of vertices, if we sample vertices in each expander, then we're pretty much guaranteed like have both one on both sides. Something like that. That's like the high level intuition. And sorry, that was the explanation was kind of long, but is that does that help?
I think it does help. Maybe Max can let us know in the chat if there's more. Yeah, I think he's happy. Do we have more questions? Or sorry, you can also elaborate.
Okay, I think like the main takeaway from expanders, like why do expanders help on in these min cut problems, is that like the min cuts cannot cut deeply into any expander because deeply then and there's like way too many edges in this cut. This cut can't be minimum because you might as well like go around the cut, something like that. Sorry, you might as well go around the expander. So that's like the intuition of why expanders help these min cut problems. Okay, that's all I have to say.
And is it easy to see that this 1 over p overhead that you were talking about for the other sampling?
Oh, the de-randomization?
Yeah.
Yeah, so let me just state the formal theorem. The theorem is suppose min cut has p terminals. Has k terminals. So sample randomized sample probably p equals 1 over k, and deterministic is we have like a polynomial of 1 over p, which is polynomial k overhead. And so that's the formal statement. And this, okay, it's not easy to see why this is true. Like the construction is based on this notion of splitters from de-randomization. I don't have much intuition of why splitters exist, but like the high level intuition of like why this is even possible is that like, I mean, in the case where p is like 1/2, sorry, in the case let's imagine k is like 2. Like it's like when k is 1, it's just like minimized isolating cuts. Let's imagine the case k equals 2. Then it turns out like you can just have like a 2-wise independent. A 2-wise independent hash family will work for that. Does that make sense, or am I completely mistaken?
Yeah, I think so.
Yeah. So like it kind of makes sense that you can push this further to maybe like polylogin. So like maybe there's 10 terminals on the one, then on the smaller side you can have like a 10-wise independent hash family, and this intuitively you can expect it to be pushed to like polylogin, but no further. So that's like I guess that's my explanation.
Yeah. Oh, all right. Thank you very much. So I think we do have time for one more question if anybody wants to. Can you mention, oh, Max had a follow-up question, why the not cutting deeply into an expander is true for weighted graphs?
Oh, I see. Okay, I can. So oh, I see. I think are you comparing the result with like Karashi and Thorop's original result, which only worked for like unweighted simple graphs? Is that the question? Is that like the
Yeah,
you're
I
trying to
think
ask?
that's yeah.
Okay. Yeah. Yeah, I think the reason is quite simple. It's just that. So let's assume we have global min cut for now. Oh, I see. Okay, maybe your question is like, how do we? Okay, I think the answer kind of relies on like what specific notion of expansion we're looking at. But let's say just imagine that let's imagine a case where all the vertices are terminals. So we're in the global min cut setting, and and here I want to claim that the global min cut cannot cut deeply into any expander, even for weighted graphs. So essentially, the intuition, the proof even is just suppose you have a cut of the graph. So like, so each vertex here, so for each vertex on the smaller side of the cut, the degree cut is a valid cut of the graph, right? So like if you can like just take a singleton cut of each of the vertices here. So basically each vertex has degree at least lambda. Let's say lambda is the min cut value. So at least lambda. But on the other hand, so that means that the volume of this side is just lambda times the number of vertices. So like volume equals like lambda times it's at least lambda times times size. But we know that this cut has the most lambda vertices. This cut has exactly lambda edges, and the graph is expanding, which means size cannot be too large. Otherwise, you do take expansion plus the fact that we have the volume of the smaller side, the volume is big, and you essentially get a contradiction. So I think.
Okay, so I actually don't know when this timer
Does that answer the
reaches
question?
0 minutes what happens exactly. So to be safe, let's thank Jason once again while we still have a minute left, and let's see if we have time for even more questions.
I mean, I'm still around after the talk.
Okay, very good. So we have this tables afterwards, so maybe we'll just save further questions for that, so you can go into little video chats.
Okay.
So thank you once again, Jason. That was wonderful and very exciting stuff.
Thanks for hosting me as well.
So now I think Ming will close the session. We'll